One of the interesting products of a kinetic study of a reaction is that we can determine what is referred to as the reaction mechanism. So to begin with, we're going to contrast the balanced chemical equation for a reaction with the reaction mechanism. So a balanced chemical equation describes the changes in amounts of products and reactants as a reaction progresses. So the reaction 2A plus 3B gives A2B3 is interpreted as being that 2 moles of A combines with 3 moles of B to produce 1 mole of A2B3. What's important to recognize is that a balanced chemical equation doesn't describe the way in which the molecules, ions, or atoms physically come together. So this reaction cannot be read as 2A collide with 3B to give 1 A2B3. A reaction mechanism is different. A reaction mechanism describes the interactions that occur between the various species as a reaction progresses. That is, it describes the actual molecular and atomic collisions that occur. So a reaction mechanism is described by a series of what are referred to as elementary steps, which when you add them together give the overall reaction. And each of the elementary steps describes a real physical process or an actual collision between different chemical species. So in the reaction that I had before, I've broken it down into a 1, 2, 3, 4 step mechanism. In the first step, 1A collides with 1B to form AB. In the second step, an A collides with the AB formed in the first step to form an A2B. In the third step, a B collides with an A2B to form A2B2. And then in the final step, a B collides with the A2B2 formed in the previous step to form our final product. And what you see is there are some things that kind of cancel out along the way. That guy cancels out with that guy. That guy cancels out with that guy. And this guy cancels out with this guy. And when we add everything together, we end up with 2 A's reacting with 1, 2, 3 B's to give our final product. But what you see is that the overall balanced equation doesn't at all tell us what the mechanism is, what the actual steps are that occur as this reaction progresses. The products of the elementary reactions that don't appear in the overall equation, and there are 3 of them here, are referred to as intermediates. So things that are made along the way but don't actually appear at the end of the reaction, intermediates. Intermediates are relatively short-lived species, and most of the time we can't isolate them, and we're just kind of hypothesizing what their identity is. Intermediates are different from catalysts, which also don't appear in our overall balanced equation, in that catalysts are not products of any of the one elementary step. They're things that we add right at the beginning of the reaction. Elementary steps describe actual molecular events. An important property of an elementary step is what we call the molecularity of the step, and that's just how many particles are colliding in that particular step. When we have 2 particles colliding, say an A and a B, we call that bimolecular. If we have just 1 particle involved in an elementary step, we call that unimolecular. If we have 3 particles involved in an elementary step, we call it termolecular. If we have 2 particles involved in an elementary step, as we mentioned previously, we call it bimolecular. Now, some things are more common than others. Termolecular steps, where we have 3 particles, are extremely uncommon. And the reason is that it's very hard to get 3 particles coming together all with the correct orientation and the correct energy. Much more difficult to achieve that than getting 2 particles to come together. And in fact, some people say, well, are there any elementary steps involving 4, 5 or higher numbers of particles? As far as I can tell, and I had a look recently, we've never observed elementary steps involving 4 particles because the likelihood of those particles coming together with the correct orientation and energy is just so low. So here's a reaction involving the decomposition of NO2. So the overall reaction is that 2 moles of NO2 decomposes to form 2 moles of NO and 1 mole of O2. The mechanism is known to have 2 elementary steps. The first step is bimolecular, where 2 NO2s decompose to give 1 NO and an NO3. And I was like, oh, immediately, NO3 doesn't appear in our final equation, so it must be an intermediate. Okay. So I've got kind of, something going on there. In the second step, the NO3 produced in the first step decomposes to give NO and O2. And if I add these guys together, what I see is the NO3 cancels out, and I'm left with my overall balanced equation. So what is the molecularity of each of these steps here? In the first step, I've got 2 particles involved, so it's bimolecular. In the second step, I only have 1 particle involved, so it's unimolecular. Note that whether it's uni, bi, or termolecular only depends on whether there is 1, 2, or 3 particles involved. It doesn't mean that they have to be different types of particles. So here I've got 2 of the same particle involved in this step, but it is still bimolecular. Every step in a reaction mechanism will have its own transition state and its own activation energy. And the important thing to recognize is that the bigger the activation energy of a reaction, the slower that reaction will be at a given temperature. So when I'm looking at one of these energy diagrams describing a reaction, I can see that there's 2 peaks here, 2 transition states, so I know that my reaction involves 2 elementary steps. And I can see that the activation energy for step 1 is a lot bigger than the activation energy for step 2. And so that tells me that step 1 is going to be fairly slow and step 2 is going to be fairly quick. Now this isn't an unusual situation to have one step being a lot slower than the others. So in this example, I'm going to draw the energy profile for an exothermic reaction with a 2-step mechanism that has the fast initial step and a slow second step. So what that's really telling me is that the activation energy for my first step has to be less than the activation energy for my second step. And because it's exothermic, and that means energy is being lost, that the energy of my reactants has to be greater than the energy of my products. So I put my reactants on the far left and I put my products on the far right, and I made certain that my enthalpy of this reaction was such that my products were at lower energy than my reactants. Now I know it's a 2-step mechanism, so I've got 2 transition states, and I want the first step to be quick, so I gave it a relatively small activation energy, and then I want my second step to be slow, so I gave it a relatively big activation energy. Something important to realize is that intermediates are formed along the reaction pathway. So in the valley between my 2 transition states, what do I have here labeled? I've got my intermediates sitting in there. So sometimes you're given a verbal description of a reaction, you have to draw the energy diagram, and then other times you're given the energy diagram and you have to turn it into a verbal description of the reaction. So unlike the overall equation, the reaction order and rate equation of an elementary step can be figured out from the equation coefficients. So if this is my elementary step, it's unimolecular, it's just involved in one particle. Unimolecular elementary steps will be first order. Bimolecular, here's my elementary step here, it's bimolecular. Bimolecular elementary steps will be overall second order. Now in this case it's second order in one reactant because I've got two of the same particles, but if it was A plus B gives C, then my rate would be first order in each of my particles. You see that? So I illustrate that in this example here. A plus B gives AB. This is bimolecular. I've got one of these guys, one of these guys. So it is first order in both of them. Here's a term molecular step. Two A's with one B. So it's going to be second order in A and first order in B in the rate law. So we can only do this though for an elementary step. You can't deduce the rate law coefficients from an overall equation. You can only do it for an elementary step. I mentioned this before. So usually one of the elementary steps proceeds at a much slower rate than the others. So in this reaction here, here's my overall reaction. 2NO2 gives 2NO and O2. My first step is a lot slower than my second step. And so the slowest step in a chemical process, we refer to that as the rate determining step, because basically this is so slow that you can almost consider this guy here to be instantaneous. This is the one that causes the delay. So I kind of have always given this sort of story about this. Is like I was waiting for a bus one day and I saw across the street there was a guy selling hot dogs, and these were Japanese hot dogs. And I thought to myself, I wonder what a Japanese hot dog tastes like. But my bus is going to be here in like 10 minutes. So I walk across the street and I say to the guy, how long would it take you to make me a hot dog? And he says 20 seconds. I'm like, okay, no problem, 20 seconds to make a hot dog. And then he points down and says, join the line. And you suddenly realize that it only takes him 20 seconds to put a hot dog together, but you're going to be waiting 15 minutes in the line. You know, making the hot dog wasn't the rate determining step. Lining up was the rate determining step. So that's my kind of example of this. So the slowest step, the rate determining step, the rate law of that step will be the rate law for the overall reaction. So in this case, the rate law for my slowest step is that it is second order in NO2. So the rate law for my overall reaction is just equal to my rate law for my slowest step, because this guy is so fast, it's kind of irrelevant. So that was an example where the first step is the slow step. This is an example where the second step is the slow step, and it kind of gets a little bit more complicated. So in the first step, A gets turned into A reacts with B, gets converted to C, and that is quick. This would have the rate law for the first step is equal to the rate constant for the first step, and then it is first order in A and first order in B, as we have one of each of those in the elementary step. The second step, which is the rate determining step, is equal to, or the rate of that reaction is equal to the rate constant for the second step multiplied by the concentration of C. And it's first order in C because there's only one of those guys there. So it's unimolecular in the second step. So the overall rate law is given by this. The problem is that C is an intermediate. It doesn't appear in our overall equation, and there's no way of knowing its concentration. we have to give rate laws in terms of the concentrations of reactants. So the question becomes, is there a way of expressing the concentration of C somehow in terms of our reactants? Can we express it in terms of A and B? Because they're the things that we're going to know the concentration of at the start of our reaction. So, can we find a way of expressing the concentration of C in terms of the concentration of A and B? So we have to think about what happens as this reaction progresses. A and B react to form C, and that's going to be quick. So the concentration of C will build up quite quickly. The C that we make in step 1 will be consumed quite slowly in step 2. So what's going to happen is the concentration of C is going to rise pretty quickly. And so what we'll find is as the concentration of this guy goes up, it's going to start making the reverse reaction occur faster and faster. And what will happen is the rate of the forward reaction will decrease as we're using up A and B, and the rate of the reverse reaction will increase as the concentration of C builds up, and eventually they will become equal. So eventually the rate of the reverse of step 1 increases until it equals the rate of the forward reaction. So what we're really kind of saying is that here's the rate of reaction 1 in the forward direction, here's reaction 1 in the reverse direction. I've indicated that by 1 and minus 1 here. Eventually these two things will become equal. That is, the rate of the forward reaction will equal the rate of the reverse reaction. And what you can see now is I can reorganize this and get an expression for the concentration of C in terms of the concentration of A and B. So I did it. I now know that the concentration of C is equal to K1 on K minus 1 multiplied by the concentration of A times by the concentration of B. So I figured out how to express C in terms of A and B, and so now I can go back and put that into my expression in the rate determining step rate law. So the overall rate law for the reaction is given by the rate law for the slow step. There it is there. Now we determined that the concentration of C can be written as K1 on K minus 1 multiplied by the concentration of A times by the concentration of B. So if I substitute that into my into the expression for the rate law for the rate determining step, I get this guy here. Okay, so basically I'm just replacing that with that. And then what I do is kind of collect all of these constants, because, you know, when you multiply and divide a bunch of constants, you just end up with another constant. So that's what I've done there. So the rate of this reaction is equal to an overall rate constant multiplied by the concentration of A times by the concentration of B. And so that's it. I was successful. So this reaction is determined to be first order in A and first order in B. So here's one where it's kind of a more realistic reaction rather than doing A, B's and C's. We've got real things in here. So it says it is proposed that the mechanism for the decomposition of N2O5 to NO2 is. And so we've got the first step. It's labeled as being fast and reversible. It's bimolecular in N2O5. We've got our second step where the intermediate decomposes into three different things. It's unimolecular, and that's labeled as being the rate determining step. So the rate law for this guy is going to be the rate law for the overall reaction. The slow step is then followed by another fast step, which is bimolecular. And when we add these intermediate or these elementary steps together, we get the balanced overall equation. So what we want to do is figure out the rate law for my slow step, because that's going to be the rate law for my overall reaction. I've got to remember that the only thing that I can have in my rate law are my reactants. So if there are any intermediates that appear there, I have to find out a mechanism of expressing them in terms of the concentration of N2O5. So the rate law for the slow step is because there's only one of these guys, it's going to be first order in N4O2. So I have to find a way of expressing the concentration of N4O10, I think I said N4O2, N4O10 in terms of the reactants. And what I'm going to do is I'm going to recognize that because my second step is slow, the concentration of this will build up, and then that's going to kind of cause the rate of this reverse reaction to increase until it equals the rate of the forward reaction for the first step. So rate 1 for the first step, the fast step, is equal to K1 multiplied by the concentration of N2O5 squared, because there's 2 of them. The rate of that reverse reaction will be K to the rate is the rate constant for the reverse reaction, so it's K to the minus 1 multiplied by the concentration of N4O10, and there's only one of them, so that is first order. Now, because the N4O10 produced is consumed slowly, we'll obtain a situation where the rate of these two things are equal, so therefore the rate of the forward reaction for step 1 will equal the rate of the reverse reaction for step 1, and now by dividing both sides by K to the minus 1, I can get an expression for the concentration of N4O10 in terms of N2O5. So now what I'm going to do is I'm going to substitute that into the rate law for my first step. So I've still got K2, there it is, and then this whole thing here is used to substitute for the concentration of N4O10. I got that from down here. And then I group together all of my rate constants to give my overall rate constant. And there you go, you can see that this reaction is second order in N2O5. So that's kind of, checking whether a mechanism is consistent with a rate law, or finding a rate law given a mechanism are kind of standard problems. There are some other problems where you're sort of asked to propose a mechanism, which are a little tricky. So in this reaction, we've got NO2 plus carbon monoxide gives NO and CO2. And experimentally, perhaps the people did methods of initial rates, perhaps they did an integrated rate law type situation. They figure out that this reaction is second order in NO2. So what can we learn about this? Well, one of the things that we'll know is that the rate determining step of this reaction doesn't involve carbon monoxide. Because if it did, it would appear in this expression. Right? So that's something that we know. It also says the rate determining step involves two NO2s, and we know that because it's second order in NO2. We also know, because the rate determining step doesn't involve CO, that there has to be at least one fast step involving CO, because CO's got to be in there somewhere. So sometimes, once you've got a rate law, you can start kind of guessing what the mechanism might look like. So this is one that I have here. So NO2 plus carbon monoxide gives NO plus CO2, and we know experimentally that the rate is equal to K multiplied by NO2 to the second power. So there has to be a rate determining step involving two NO2s. So I'm just going to make that the first step. There we go. All right, two NO2s decomposed to give an NO3 and an NO. So basically 2 NO2s come together and one of them loses an oxygen and the other one gains it. It seems reasonable. Now, what happens? Well, the NO3, the molecule that gained an oxygen, collides with a CO, and the extra oxygen gets transferred over to the CO to make CO2. Okay, and we're going to say that that step is fast. And so when I add all of this together, the NO3 we recognize is an intermediate, and it actually works pretty good. We get kind of what we want, and then also I should point out that we lose one of our NO2s here. There we go. And so we've got NO2 plus CO gives NO and CO2. It's bimolecular, this mechanism, in NO2, so that's consistent with the observed rate law. And we've still got CO in there, but the CO, because it's in a fast step, doesn't appear in the rate law. So, you know, this getting this rate law, getting this guy here, allowed us to go ahead and propose a mechanism, and perhaps we could do further experiments to test whether this mechanism was a valid one or not.